Okay, so this will be the last example in section 3.7, optimization. And this I got from the book. I think it's number 44 in the book. So this has to do with light and how it refracts from one medium to another. So for example, if it goes through glass, the light is actually going to bend. And you've probably seen this, right? If you take a glass of water, right, a clear glass of water, and stick a pencil in it, you're going to notice that it bends, right, when you look through it. So yes, light bends through water, it bends through glass, it bends through various mediums that light travels through. And how it does that is according to what's called Snell's law. Um, it obeys this equation here, where theta 1 and theta 2 are these angles. And V1 and V2 are the speeds of the light as they travel through the two mediums. So V1 is the speed through this medium, the blue one up here, and V2 is the speed through this little pink medium down here, right? So yes, as light travels at different speeds in different mediums, and let's not get into why that is, but that's a fact of nature, right? So using the fact that light travels from one point, let's say we have a flashlight here at point P, right here, and light is going to travel from point P to point Q, way down here. It turns out that light does that so that it minimizes the amount of time that it takes to get from here to here. So the total time that it takes to travel from this point to this point should be a minimum. Now, why is that true? Again, that's a physics question. So take a course in physics. I'm sure Professor Guy will gladly explain to you why light travels on a path that minimizes the time that it takes to get there. Um, you know, I know a little bit about this. I know this is a more general principle called the principle of least action. So action is the quantity that nature wants to minimize. Um, this is one sort of feature of that general principle, but we're not going to get into that. And you can read a little bit about the history of where this came from. This is a very old idea, this law. So it's named after Snell, but it was discovered long before that, over 1,000 years ago. In any event, yeah, so we want to essentially prove this equation here, which, right, it does not seem easy. This is a very hard problem, right? This is going to be the challenge problem for this section. Right, and for a variety of reasons. One, it involves angles, right? You can see sines and cosines, so it's going to involve trigonometry as well, right? Yeah, also there's a little bit of algebra here, and it does get a little bit tedious. So I'm going to try to go through it step by step, right? So what are we trying to do here? We're trying to minimize the total time to go from point B to point Q. Right, and so we're going to assume that this picture is in the book. It's a very nice picture here because they leave nothing to the imagination here. They label all the quantities that you're going to need. X is this distance here is going to be X, right? This is A minus X. This angle here is theta 1. This angle here is theta 2. This is D1 and so on, right? And in fact, I'll do one better here, right? I'm going to use this as the triangle here. This distance here, of course, is also x, right? And if we use this triangle here, right, this distance is also a minus x, right? Okay, so yep, we're definitely going to use some trigonometry here. All right, so before we talk about the time that it takes to go from one place to the next, let's talk about how far it travels. Let's talk about the distance, right? So light's going to travel along this dashed line here. So I can't call it D1. How about if I call it S1? Okay? And then it's going to travel along this path, which could be a different distance. I'll call this S2, right? Okay. So the total distance the light travels is S1 plus S2, right? So that's for distance. But we want the amount of time that it takes, right? So I'm sure you remember that distance is just speed times time equals speed times time, right? And this is true, of course, we're talking about constant speed, and it's pretty fair to say that within each medium, light travels at a constant speed, the speed of light, right? So yeah, speed is also just distance divided by time, right? But we're solving for time here. So time is really just going to be distance divided by speed. Distance divided by speed. And I really should be using letters here, right? So D or S for distance and V for velocity, right? Even though it's a speed, we'll use V for velocity, right? And this is just time t, right? Okay, so the time that it takes to travel from point P, not to point Q yet, but just to the point where it crosses the mediums. I'll call this point O. So from point P to point O, it travels a time, I'll call it T1, which is a distance S1 divided by the speed, so that's S1, divided by the speed V1. Likewise, as it travels through medium 2, the time that it takes, T2, will be the distance S2 divided by V2. Okay? And so it's pretty clear that total time, I'll call capital T, is just the sum of the two times, right? It's the time that it takes to go from point P to point O, that's T1, plus the time it takes to go from point O to point Q, that's T2. Okay? So, right, but in terms of V, this is S1 over V1 plus S2 over V2. So is everyone okay so far? This is just, distance equals rate times time, right? And then getting the total time here. Okay, what's next? Well, S1 and S2, these are distances, right? And notice that these are triangles, right? So I'm going to use, let's use the Pythagorean theorem to get S1 in terms of x and d1. So S1 squared is just going to be x squared plus d1 squared, using this triangle here. And if it's not clear, right, this distance is also d1, right? This distance is d2 here. So I'm using essentially this triangle, right triangle here. Sorry about that. All right. And now let's do the same thing for S2. S2, a little more complicated, right? So it's a minus x squared plus d2 squared, right? So this is really just Pythagorean theorem, right? Applying it to these two triangles, right? So let's plug that in here, right? So now we have t is equal to S1. Oh, I guess we have to take the square root now, right? So S1 itself is the square root of x squared plus d1 squared, all divided by v1, plus S2, which is now the square root of this mess here. A minus x squared plus d2 squared, right, over v2 squared. Just v2, sorry. Okay, so this is t, and notice it depends on a whole bunch of things here. It depends on x, it depends on d1, depends on v1, v2, d2, and a. A is actually the distance from this point all the way to here, but it doesn't matter. A is fixed, right? So let's be clear here about what's fixed and what's not here, right? Let me do it this way here. So A, D1, D1, D2, V1, and V2 are all constants. They're all numbers. Okay? The only thing that's allowed to change here is x. Now, in the picture, it might not look like you're changing x, but to be sure, how do we know that the light travels from point P to point O, and then from point O to point Q? Light might decide to do this. It travels only to here, right? And then it goes all the way to point Q from here, okay? So in that sense, this distance x could be different, right? In fact, we really don't know where the light crosses the mediums here, right? That's what we're trying to figure out, actually, right? What is x here? So we're thinking about this t here as a function of just x, right? All these other quantities here are just numbers. They're just constants, okay? Okay, so now what? Well, we have our function t, and again, this is the quantity t we want to minimize. This is effectively our primary equation here, right? So it's not a very simple one, but it is our primary equation, okay? And it is a function of just one variable. Remember, v1, d1a, v2, d2, these are not variables. These are constants. These are fixed numbers in this problem. We don't know what they are necessarily. We can plug those in later, but they're just considered constants. Okay? All right. So we have our primary equation, and we want to minimize, right? Well, how do we know we want to minimize instead of maximize? We want the least amount of time, right? So if we're looking for the least of something, we're trying to find the smallest or minimize it, right? Okay. So how do you minimize a function? Well, find the critical numbers, right? Take the derivative, or if you prefer, t prime of x, and set it equal to 0. So this does not look easy, right? We want to take the derivative of this with respect to x, right? The key thing to remember is that the v1, the d1, these are all constants, right? So the easiest way is to turn this into to the power 1/2 and use the chain rule, right? So we're going to get, first of all, v is a constant, so let's just think of this as 1 over v1 times this mess here. So if this is to the power 1/2, we're just going to get 1/2 times x squared plus d1 squared to the negative 1/2. And then don't forget the chain rule. The derivative of this, right, is 2x. Okay. So you can see this 2 cancels with this 2. Right, so let's simplify this later. We still have to, right, using the sum rule, take the derivative of this second term here. And it's done the same way, right? We have 1 over v2 times a big mess here, right? So we're going to get all of this to the negative 1/2 power. So a minus x squared plus d2 squared to the power negative 1/2, all times the derivative of this. And the derivative of this will be 2 times a minus x. But be careful, there's another chain rule here. The derivative of a minus x is actually negative 1. Yeah, tricky, right? So this is fairly complicated. So this is going to be a little bit of algebra. So let's go through it. So we already mentioned the 2's cancel. The x did not cancel. The x is actually the only thing left in the numerator here. Because in the denominator we have v1, and then we also have this square root here, right? v1 times the square root of x squared plus d1 squared. Okay, remember it's negative 1/2, so it's downstairs, right? Plus, or actually minus, right? So I'm going to take this negative and bring it all the way in front to make that a minus, right? And we get a similar thing here. The numerator here is just a minus x. Oh, the 2's cancel. And, yep. And so the numerator is a minus x. And the denominator is just v2 times the square root of everything in the parentheses here, a minus x squared plus d2 squared. Okay. So, all right, so that's the derivative, t prime of x, right? And to find the critical numbers, we set this equal to 0 and solve for x. Now that is easier said than done. In fact, we're not going to do that, right? We could spend probably the next 45 minutes, maybe an hour, actually solving this for x, and it's going to be a mess. And if you're not careful, that might be what you're kind of, what you're accustomed to doing, saying, well, I have to solve for x in terms of all these other variables. Honestly, that might take me an hour. So that's kind of not the point of the problem. But if you're not careful, that might be what you try to do here. So no, we're not actually going to do that here. We're going to go back to the geometry of the problem here, or maybe I should say trigonometry of the problem here. Right, so let's take a step back and just notice something. What are we trying to prove here? We're trying to prove this equation here that has to do with v1 and v2 and theta 1 and theta 2. Notice that none of this down here has anything to do with theta, or theta 1 or theta 2. Okay, so solving for x here is actually not going to help whatsoever in trying to show this equation here, the Snell's law here. Okay, so instead what we want to do is use the geometry of this, right? So theta 1 is an angle of this triangle here. In fact, let me see if I can draw this triangle down here where I might be able to do a little bit better job of this. Okay, so this is S1, this is D1, this is X, and then this angle here is theta 1. I should put S1 on the outside here, sorry about that. Okay, so that's our triangle. And what do we want? Well, we want the sine of the angle, right? So what's the sine of theta 1 here? Can we calculate the sine of theta 1? So do you remember from pre-calculus, SOHCAHTOA? Just a quick refresher on that. Right. Sine is opposite over hypotenuse, right? Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. But we're looking for sine. We need opposite over hypotenuse. The opposite side to this angle is x. That's opposite over hypotenuse. The hypotenuse is S1. Right? So that's the sine of theta 1. But remember what S1 is. S1 is, well, this is S1 squared. S1 is the square root of x squared plus d1 squared, right? So sine of theta 1 is x divided by the square root of x squared plus d1 squared. Okay? All right. Now we're going to use, okay, let's hang on to this thought for a minute here. Well, let's go on to the next triangle, and I'm going to draw that down here since I'm running out of space. Can I draw it in this color here? So the triangle here, yep, is going to look like this. All right, so this should be a right triangle. Sorry about that. Right, so this distance was a minus x. This distance is S2. This distance is D2. And theta 2 is this angle here. Okay. Okay. So in this case, sine of theta 2 is going to equal opposite over, wait a minute, that's not theta 2. Oops, I drew it wrong. All right, give me a minute. I can fix this pretty quickly here. Yep, I drew the triangle wrong. All right, let me draw it again. So here's D2. Wait a minute. I need a... Yeah, okay. Got it now. Had to look at it several times. Right, so yep, this is D2 here. Down here, it's the same as this length here. It's a minus x. And then this side here is S2. This is theta 2. I had this as my theta 2, so that's the wrong theta. Okay. Okay, so, all right, so now sine of theta 2, sine of theta 2 is going to be opposite, which is a minus x, over hypotenuse, which is S2. But the hypotenuse S2 is We go back up here. The square root of this quantity here, right? A minus x squared plus d2 squared. So let's write that down. A minus x over the square root of a minus x squared plus d2 squared. Okay, so that's sine of theta 2. Right? So this is just trigonometry, right? SOHCAHTOA. Okay, now what? Well, let's go back to the expression here for t prime of x, right? This is the derivative of the time with respect to x. And let me just write it in a slightly different way here. This is still the same thing as 1 over v1 times x over the square root of x squared plus d1 squared. It's an x. Minus 1 over v2 times a minus x over the square root of a minus x squared plus d2 squared. And I think you can see now why I wrote it this way. In fact, hopefully you were way ahead of me here. Let's look at sine of theta 1, right? Sine of theta 1 is this quantity here. And this should look very familiar. This thing here looks an awful lot like this thing here. In fact, they're identical, right? They don't just look alike, they are the same thing, right? And likewise, this mess here, this big fraction here, is the same as this big fraction here, which is also the same as sine of theta 2. Okay, so now we get 1 over v1 times sine of, this is theta 1 here, right? Sine of theta 1 divided by v1 minus, and then this fraction here is the same as sine of theta 2 divided by v2. Okay. Now remember, what were we trying to do? We're trying to minimize the time. So to find the critical numbers, you take the derivative. We painfully did that here. It took a while, but we got the derivative. And we set it equal to 0. Well, if you just add this term to both sides, I think we get our answer here. So the sine of theta 1 divided by v1 has to equal the sine of theta 2 divided by v2, which, if you remember, that's the thing we wanted to prove, right? This goes by the name of Snell's law, right? Right. I mean, Snell is the person that got credit for it, but suffice it to say, a lot of people figured this out even long before Snell did. But that's what we wanted to prove, right? Remember, the original problem was, so this is called refraction according to Snell's law, and we wanted to use the fact that light travels from P to Q to prove Snell's law. So we actually did prove this equation here, just using the fact that time, or rather light, travels from one point to another in the least amount of time, where we minimized the time, right? So, yep. So by setting this equal to 0, we minimized the time that light travels. And this, right, and as a result, we get this equation relating the thetas and the v's, the speed of light traveling through different media. So like I say, this was kind of my favorite problem here, and I know it. This, you might have to think about this a little bit more, but it is quite nice. It's quite ingenious to get this result just based on this very general principle called the principle of least time, or the principle of least action in general. Right, so that said, like I say, this is a challenge problem, right? This is a very difficult problem. And I hope at least talking you through step by step, maybe it makes a little more sense now, maybe not. And if it doesn't, you know what? In the end, this is not going to be a test question. Obviously, this is just something to think about, a fun little challenge problem. but it's worth going through, right? Maybe just going through once. And the idea is, if you can handle this, if you can do a problem like this, you should be able to do any reasonable problem like the previous ones that we did. That could be on a test. So the previous 2 or 3 problems we did are very reasonable test questions. This is not a reasonable test question, I think. You know, I mean, maybe for extra credit, but honestly, at this point, we're not worried about that here. So I hope you enjoyed this. Well, I know I did, but I guess that's just me. I'm weird, but so yeah, I'll leave it at that. And just to say that I hope you enjoyed this. If not, well, you're never going to have to see it again, unless you take physics, in which case you probably will see something like this again.